This video is going to go over the Hess's Law lab to make sure that you did it correct before your FRQ tomorrow. So procedure 1, I'm going to use fake numbers. So my numbers might not look anything like yours. So you're supposed to get about 2 grams of NaOH. I'm going to say I got 2.02 grams of NaOH. And then you added it to 100 milliliters of water. And you should have recorded a temperature change. Initial temperature, I'm going to say mine was 22 degrees Celsius. My final temperature was 25 degrees Celsius. Again, I'm making these numbers up. So my change in temp, TF minus TI, would be 3 degrees. And so looking at the analysis questions kind of guided you on what to do. So first thing, calculate your delta T. Done. Second, calculate the mass of solution that was absorbed for each reaction. And then it told you to use water as the density. So going back to your calorimetry lab, the thing we did in the computer lab for 2 days. In this lab, you added an ionic compound to water. That is exactly what you did in part A of the online lab. And so I told you to use this to help you. So you got your delta T, and then it says we're going to calculate how to calculate delta H, what we're doing. The mass should be the combined mass of the salt and the water. So in my lab, I had 100 milliliters of water. Now, the density of water is 1 gram per milliliter, so 100 milliliters of water is 100 grams. And then I also had 2.02 grams of NaOH. So that combined mass is 102.02 grams. So again, as the lab handout told you, when you have an ionic compound in water, you combine them for the mass. And then use the specific heat of water. And I think it told you that in the lab anyway. The specific heat of water is 4.18 joules per gram times degrees Celsius. Okay, and so we found M, check, that was number 8. Number 9, calculate the heat absorbed by the solution. So Q is heat, MC delta T. My mass, 102.02 grams times the specific heat, 4.18 joules per gram times degrees Celsius, times my delta T, which was 3. And I go multiply all of those. And that gives me Q equals 1279 joules. Now, anytime you have heat, or you take a temperature, you always get the temperature of the surroundings, never the system. And so if that's the temperature of the surroundings, this is the Q of the surroundings. To make it the heat of the system, of the chemicals, you have to flip the sign. So Q of my system is negative 1000 joule. And that was what number 10 asked. So the heat released by the reaction. Boom. That many joules. And so I can tell you right now, because my system's heat is negative, this is an exothermic change. And that should make sense to you because you know exothermic changes feel hot. Well, this change, the temperature went up. It felt hot because that system was giving off heat. Okay. And then 11, calculate the moles of NaOH. So in my example, I had 2.02 grams of NaOH. To go from grams to moles, you need to use your periodic table. And so sodium is like a 22.9, oxygen is 16, hydrogen 1.08. So the molar mass of NaOH is 39.998 grams. So that was my fake example. I used 0.51 moles of sodium hydroxide. Okay, and now let's look at what comes next. You find your moles of sodium hydroxide. Determine the heat change for the solution, or your delta H. Now, you should know delta H is kilojoules per mole of reaction. So right now, my reaction is in joules, negative 1279 joules. I got to divide that by 1,000 to make it kilojoules. So negative 1.279 kilojoules, and divide that by my moles, which is 0.051 moles of NaOH. Now, when you have something dissolved in water, there's not a balanced equation to write, and so your moles of your salt, that is like saying moles of reaction because we're dissolving this. And so you don't have to like do another step when it is dissolving in water. And that would be negative 25.1 kilojoules per mole for the delta H for part 1. With my fake numbers. Part 2 was, what happened in part 2? Part 2, you measured out, you didn't use water, instead you used HCl, and you used 100 milliliters of 0.5 m HCl. So we have a salt in a solution this time. And my salt, we said do the same thing again. So let's say I had, for simplicity's sake, 2.02 grams of NaOH. Now, you can make the assumption, it tells you, make the assumption to solve for delta H, that your mass of HCl, you're going to use the density of water. It's got a low molarity, 0.5 is not very much, and so that would be 100 grams. And then 2.02 grams of NaOH. So again, my mass is going to be the same value. And again, that's just because I want to make it easy. So yours probably is not the same because I doubt you have the exact same NaOH masses for each trial. I have my mass, and then let's say my delta T for this one, it doesn't matter, but my change in temperature, my final minus initial, it should have gotten hotter, was like 4.2 degrees Celsius. Again, I'm making that number up. And so next, to solve for delta H, we need to solve for our Q. Q equals MC delta T, and it said to use the specific heat of water, which we are. So Q equals my mass, 102.02 grams, times the specific heat of water, times your change in temperature for this one, 4.2. And that Q is 1791.06312. Yada yada. I don't know why I wrote all those numbers. 1791 joules. And just as we said before, this is the Q of the surroundings. So the Q of the system is negative 1791 joules. And we know we're going to have to change that to kilojoules, so negative 1.79 kilojoules. Okay, now we should stop because it's water and think a little bit about moles. So you mix sodium hydroxide and HCl. And when you mix that, you make water and sodium chloride. Now, which one determined how much product we made? We need to think about our limiting reactant. You had 2.02 grams of this, and you would need to change that to moles. Okay, well, it's the same number as the one before, but you would go change it to moles, and that would be 0.051 moles. Okay, and then HCl, we had 100 milliliters of 0.5 molar. So I need to figure out how many moles of HCl that is. So 0.5 molarity, moles over liters, so over 0.1. Moles, 0.05. Yes. So we had 0.05 moles of each one. Now looking at this equation is all 1-to-1. There are no coefficients in this, so they're both limiting. In your example, you might have, these are pretty much the same number, but your moles might be different than mine. And so double check your moles and go with the smaller number. Just so happens in my made-up numbers they're the same, but that won't necessarily be the case in yours. So whichever moles is smaller, use that value for your delta H. So delta H equals, what was that? Negative 1.79 kilojoules over 0.05 moles. And again, it doesn't really matter. Mine, I guess, was technically HCl, if you had measured it perfectly. And then this, we did have a reaction happen to this one because you mixed two different things. And so I want my delta H unit to be kilojoules per mole of reaction. This is kilojoules per mole of HCl. So looking at my balanced equation, for every one of these reactions, I have 1 mole of HCl. And so I need to get rid of this unit, mole HCl. I do that by putting up top 1 mole HCl and 1 mole of reaction. Now that cancels that unit out, and I have the units that I want. But make sure you don't forget about the numbers. And so this one would be negative 35.8 kilojoules per mole of reaction. Now again, I got this 1 right here because my balanced equation was a 1. If it wasn't a 1 right here, I would have to put whatever this number is up here. But it was a 1, that's why I wrote a 1. But it should always be 1 mole of reaction at the bottom. Okay, and that is part 2. Part 3, you were mixing 2 solutions. Part 3 was just like in the lab, the online lab that we did, this part. Solutions in an aqueous solution. So got our delta T, and then it says your mass is your combined mass of both solutions. And so in this one you had 50 milliliters of each, so that's total 100 milliliters or 100 grams. That's my mass value that I'm going to use. My delta T, whatever, you have that. And so your Q, you would do the same thing as before. So 100 grams times the specific heat of water times whatever your delta T is. Let's say mine's 3. It doesn't matter. My Q is 1254 joules. Flip it for the system. So negative 1254 joules or negative 1.254 kilojoules. And then we do need to think about moles. This lab was set up nice, so it's all 1-to-1, and you had the same amount of each one. And so we had the same amount of moles of each one, so there wasn't a limiting. On the FRQ, there might be a limiting. You most definitely would want to double check that, but these are the same numbers, so it's going to be the same number of moles. So 1 molar of moles over liters. 50 milliliters, make sure you divide that by 1,000 before you put it on the bottom, is 0.5. So my moles were 0.05 moles of each one. And everything in this equation is 1-to-1, so it's going to be like the last problem you divide by your mole value to get your delta H. Now make sure on the FRQ that you watch for your limiting and you watch your coefficients.